So here we're going to talk about the kinetic molecular theory of gases. So this will help explain some of the gas laws and some of the application to these gas laws. We'll talk about the actual gas molecular speed and then some of these effects associated with gases like diffusion and effusion. So the kinetic molecular theory of gases, this helps explain how the molecular nature of gases, which gives rise to the macroscopic properties. So we're just going to start looking at it in terms of gases as individual molecules instead of these like large features like volume and stuff like that. So there are some assumptions that go into this kinetic molecular theory. Some of these assumptions, we're going to talk about these four of them. So one, a gas is composed of particles that are separated by a lot of volume, a lot of distance. They are not very close to each other. So the volume occupied by individual molecules is negligible. So when we talk about the volume of a space, or the volume that a gas occupies, the gas is occupying that space, but the individual molecules or atoms are taking up a negligible amount of that space since they're so spread out. Another assumption is that gas molecules are constantly in random motion. They move in a straight path, they collide with the walls of their container and with one another in perfectly elastic collisions, meaning that the energy is transferred but not lost in the collisions. So an example of that would be, if you smash two things of like silly putty together, they would kind of crumple. And that would be an inelastic collision. An elastic collision would be more like billiard balls that hit each other, and they can transfer the vast majority of their energy to the other molecule, in this case the other ball, right? So this is an assumption that we have. Also, we assume that gas molecules do not really exert attractive or repulsive forces on one another, and again, that's also partly because we're saying that they're so spread out. And then lastly, we talk about the average kinetic energy of gas molecules, and we say that is proportional to the absolute temperature. Okay, so the average kinetic energy proportional to the temperature. So you increase the temperature, you're going to increase molecular motion, increase the average kinetic energy associated with those molecules. So the kinetic energy is also 1/2 mv squared. This, I know it says u, but mass times velocity squared. Here we're talking about velocity and we're using a u just because v already has volume and some other things associated with it. And sometimes this u squared, we talk about it in terms of the mean square speed. So the mean square speed being the speed of all of the individual molecules squared and divided by the number of those molecules. All right, so in terms of understanding these macroscopic properties, this kinetic molecular theory helps us to describe some of those. One of them would be compressibility. So gases are compressible because molecules in the gas phase are separated by very large distances, which was that assumption number one on the prior slide. They can be moved closer to each other by decreasing the volume occupied by a sample, which you can do with a gas, but it is very hard to do with something like a liquid or a solid since there is not a lot of space between those molecules, where with gases there is a ton of space between them. So that's how and why we can compress gases. So this makes some sense in the context of kinetic molecular theory of gases. And we can also use it to describe the four laws that we talked about. If you remember Boyle's, Avogadro's, and Charles' law, these were the simple gas laws, so to speak. And then kind of the different one was Dalton's law of partial pressures, which we had talked about in gas mixtures. So, and I had alluded to some of these ideas in the past as well, but let's start with Boyle's law. So remember, volume is inversely proportional to the pressure. So the pressure exerted by a gas is the result of the collision of gas molecules with the walls of their container, which is assumption number two. Therefore, like the magnitude of the pressure depends both on the frequency of collision and the speed of the molecules when they collide with the walls. So if you're going to decrease the volume occupied by a sample, the frequency of these collisions will increase the pressure. You're going to increase the frequency of those collisions, right? So this kind of in the context of makes sense. In Avogadro's law, volume being proportional to the number of moles of gas. So the magnitude of the pressure exerted by a sample of gas depends on the frequency of the collisions with the container of the wall. So if you have more molecules, you'll have more pressure, right? That would increase the volume essentially, right? So that's why this makes some sense. Charles' law, volume proportional to the temperature. So the heating of the sample increases its average kinetic energy, which was assumption number 4. Upon increasing that average kinetic energy, that's going to mean there's also an increase in the speed of those molecules, the mean square speed of the molecules. So since those molecules move faster, they're going to hit the walls of the container more frequently, and therefore increase the volume of the container, right? Increase the pressure or increase volume of the container. All right, and then Dalton's law of partial pressures. I think when I was talking about this in gas mixtures, I did allude to this as well. So gas molecules do not attract or repel one another, which is assumption number 3. So the pressure exerted by one gas is unaffected by the presence of another gas. So consequently, the total pressure exerted by a mixture of gases is simply the sum of the partial pressures of the individual components of the mixture. So yeah, if you're thinking about the partial pressure in terms of when a gas in particular is hitting a surface, it's just proportional to the amount of moles of those gases that are present. So again, these all do make sense when you actually look at the molecular level, as opposed to just the macro level, which is what we had focused on previously. All right, so molecular speed. We will talk about this in terms of root mean squared speed. So it's U with a sub RMS, root mean squared. Don't worry too much about what this means exactly. I would rather just take a look at these examples below. So as you increase the temperature, of a gas, so here we have nitrogen gas. If you increase the temperature, this is the molecular speeds that you would see. The root mean squared, just think about it as like the mean. So you see at 100 Kelvin, most of the molecules are going at, let's say, like 250 meters per second. You increase it to 300 Kelvin, and you can see that this spreads out. And so you have some molecules that are traveling much faster than others. Some are traveling really slow, some are traveling faster. And they are constantly colliding, so they're imparting energy to each other and things like that. But you can see that the average is moving up. So you increase the temperature, you increase the average speed. That would be something that you should definitely know. Okay, go up to 700 Kelvin and even much higher average molecular speed. And again, we talk about molecular speed with root mean squared speed, but you can just think about it in terms of the average speed is totally fine. So this was all for nitrogen gas. Similarly, the weight of this gas matters as well. So remember that kinetic energy is 1/2 mv squared. The mass will matter. So the velocity will change. Even though all three of these gases at 300 Kelvin have this same average kinetic energy, but that does not mean they have the same average speed. Okay, so helium is much smaller. So if it's 1/2 mass times velocity squared, its mass is much smaller. So if it has to have the same 1/2 mass velocity squared as N2 and 1/2 mass velocity squared as Cl2, it needs to be traveling much faster. So since it's lighter, it's traveling much, much faster at the same temperature as something that's much larger, like chlorine gas. So chlorine gas is traveling at much slower speed, but chlorine gas here has the same kinetic energy as helium. Because of, again, the kinetic energy equal 1/2 mass times the velocity squared. So this is again something that you're going to need to know. So this is keeping the temperature constant but changing the molar mass of the gas. Here is keeping the molar mass of the gas constant but changing the temperature. And so you can see these trends here. We can actually calculate the root mean squared. The root mean squared is the square root of 3RT. So you can see it's based on the temperature divided by the molar mass, which is that scripted capital M. Very unfortunately, this uses the other R, one of the other R's, so joules per mole times Kelvin, so 8.314. So that makes this a little tricky. We're still dealing with a gas, but you're using a slightly different gas constant. The thing that's really perturbing to me and upsetting to me is molarity, or so sorry, not molarity, molar mass is in kilograms per mole in these situations. We have never seen molar mass in kilograms per mole, and we will never see it in kilograms mole per again. So this is really dumb. So I don't actually really care about calculating this, but just know that just in terms of how it's inversely proportional to the molar mass is really what matters, right? Just the bigger things travel slower. That's really all that this really needs to tell you. And then that temperature, it's proportional to temperature. So you increase temperature, you increase speed. So really those are the two trends that you should really know. All right, so along with molecular speed, there are some other features that come out with gases. So one of them is diffusion. So this is the mixing of gases as a result of random motion and frequent collisions. So here, let's say you had two well, let's talk about effusion also. So effusion is escape of a gas molecule from a container to a region of vacuum. So this would be this situation where you have a gas, it's escaping into a vacuum. That's called effusion. Diffusion is the mixing. So if they're both sides of the containers had different gases, like in this situation, and you were to open up this container, they would mix fairly rapidly in general. And again, that's just because they're bouncing all over, they're running into each other. At some point, some of them would migrate across to the other side, and then you'd get this homogeneous mixture. Same thing with this. If there's nothing in here, this gas would effuse across through this hole. Just because it's bouncing around, at some random point, the molecule would be able to go through here, so on and so forth. This brings up this idea of these gases will not do this at the same rate under all scenarios. So first of all, if you think about it in terms of that, these things are bouncing around. If you increase the temperature, this mixing will happen quicker, right? Because they're bouncing around more quickly. Same thing with this. If this is a higher temperature, it's bouncing around more quickly, so it will effuse faster. But also we can talk about the rate of effusion or diffusion for different gases, so different gas types. So instead of just the temperature, think about it in terms of the types of gases that we're referring to. And this is called Graham's law. So the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molar mass. So the rate inversely proportional to the square root of its molar mass. And this makes a ton of sense just based on what we had talked about in terms of the average speed. This is just saying that the things that are heavier are going to effuse or diffuse slower. And that makes sense, right? It's traveling at a slower speed given a constant temperature. So it's going to take longer for that to bounce around and at some point make it through this hole, or bounce around in here and at some point make it through to the other chamber, right? So we can look at these rates and you can set them equal to each other like this. So you can say the root mean squared of one over the root mean squared velocity of the other is the square root of the inverse of their, or the square root of the ratio of their molar masses, okay? So that's called Graham's law. So the main thing is conceptually understanding that, again, with the idea of kinetic molecular theory of gases, just knowing how temperature or molar mass will change the rate of effusion or diffusion, and also change the velocity or change the kinetic energy, for example. Okay, so let's try one of these. Determine how much faster a helium atom moves on average than a carbon dioxide molecule at the same temperature. So we want to look at the ratio of their root mean squared. This is going to be based on the square root of their molar masses. So root mean squared of helium over root mean squared of CO2 means helium will be 3.316 times faster on average than CO2, where we just take the molar masses, the square roots of each other, like so. So even though this is 10 times heavier, 11 times heavier, it ends up being 3.316 times faster because that's the square root of roughly 10. So